h squared. Here. Good. Yeah. So that's what we computed this morning, that delta mh squared is 3 lambda squared over 16 pi squared v squared, and 2 mw squared plus mz squared plus mh. So there were questions whether it's the same h, capital H and little h. Yes, they are the same. Minus 4 mt squared. Right? Maybe during the seminar we'll find another way to actually obtain this result, without computing Feynman diagrams, by simply computing what is called the Coleman-Weinberg potential. So this gives you actually a direct analytic expression, of this expression there, right? Which is related to the supertrace of the spectrum that depend on the value of h. And we'll see that this is a nice way to really capture this quadratic divergence. We will see that. There is a little subtlety here that is quite interesting to look at in details, what is the contribution of the ghost sort, for instance. Nonetheless, so the problem was a numerical problem. Let's say that when you put some numbers, this quadratic divergence is something of this order. Right? For a cutoff of 1 TeV, you get already the expected value of the X mass. So this means that if you increase lambda, let's say, you have to fine-tune the quantum correction, delta mh, over the 3-level contribution to the mass in order to make sure that the physical X mass, so mh physical, let's say, physical, the one that you can measure in your collider, is a 3-level mass, 0, plus the delta mh squared. So the problem is clearly that if this quantity is much larger than this one, then you need a cancellation between those two things, which is unlikely or unnatural or whatever you want to say. So this morning, I already explained various ways to actually cancel or reduce these quadratic divergences. The first one was using the Goldstone theorem. So really seeing the X as a pseudo-Goldstone boson, what we call PGB, a pseudo-Goldstone boson. Maybe you can also say pseudo-Nambu-Goldstone boson, PNGB. Sometimes there is N. And the other approach was relying basically on quantum mechanics, and quantum mechanics, you needed to extend basically the symmetry of the standard model. So you either need to introduce supersymmetry, basically to give a chirality to the X boson. So then you have the X left and the X right in a sense. Or you can use Lorentz transformation in higher dimensional space. Lorentz symmetry in D greater or equal than 5. Right? So this way you are making the connection with spin 1/2. In this case, you are making a transformation between the scalar and spin 1. Right? Good. Is there any other model that try to access the hierarchy problem? Yes, there is a long list of things that people have tried. Right? So the first idea actually was from Veltman alone, from Veltman itself, and he said, well, we have a quadratic divergences, but maybe the coefficient in front of these quadratic divergences cancel itself. Right? So this is what is called the Veltman fraught. So that's Veltman. I don't remember in which year he proposed these things, but he said, well, okay, if the X mass is such a way that this term is actually vanishing, then I don't have any quadratic divergences. And it was a prediction of the X mass, right? So it predicted that the X mass should be 320 GeV. I haven't done any mistake. If you're solving this equation, it should give you this. Okay, so that's maybe the simplest solution of the hierarchy problem, except that it's not a solution at all. It's just a nonsense. It's a nonsense for various reasons. First of all, because it seems that it's a solution only at the one loop level. If you do the computation at two loop, these things totally disappear. It's a nonsense also because here, okay, I introduce a cutoff and I use the same cutoff for all the particles, right? For the W, the Z, the top, the X. And if you don't have any symmetry between all these particles, I mean, there is no reason why you should use strictly the same cutoff for all these particles. So this means that without any symmetry, there is no reason a priori that this number here in front of these things are exact numbers. I mean, they are exactly related to each other. So this means that there is no real meaning to this equation.
And in this expression in the brackets, when you write mx, this is mx0.
Yes, right. Here is always a tree-level expression, right? So the Veltman idea was totally nonsense. It's okay, you can make some mistake in your life. If you do some good stuff, otherwise it's fine. Nobody will blame you. What else? The spin trick. The other idea is the composite X idea. So composite X. So somehow here, when we are doing this computation, we have assumed that the X is a real field, a real scalar field up to arbitrarily high energy. So you were using the X as a point-like particle up to infinitely heavy energy. But it doesn't have to be the case. If the X is a composite object, you see really the scalar field up to energy at which you will see the fundamental constituent. So this means that when you are computing these loop integrals, actually you should include a form factor to say that the X will become a broad object as soon as you are reaching energy where you will see the interior of the X boson. So in this case, you have some form factor that will actually regularize these quadratic divergences. So this means that in this case, I mean, you should expect contribution to the mass of the X, which is not proportional to lambda squared, but that will be proportional, delta NH squared will be proportional to the composite net scale of the X boson. So that's still a viable idea, and we will look a little bit more at the phenomenology and some concrete example of this composite X idea and see what are the phenomenological prediction. The fifth idea was
Christophe, excuse me.
Yes.
The number 1 and number 4 are not related to each other.
They are, I mean, at the end of the day,
Quite close, right?
if you want to have a realistic composite X model, you need to explain why the mass of the X is actually smaller than the strong coupling scale. So you're producing resonances by strong interaction, but you still want to have a mass gap between the mass of the X and the mass of the strong sector. So this means that most likely the composite, but it's also pseudo-Boston boson. So yes, so there is a tight connection between those two. But that's more like an experimental fact. It's simply because it's not possible to have the mass of the X exactly at the mass of the strong interaction because we haven't seen all the resonances of the strong sector. So that's really a phenomenological issue that forces you to go into this regime. So fifth solution to the hierarchy problem has to do with things that I don't really understand, which is related to quantum gravity. And people are telling you that actually, if m Planck is a scale of of quantum gravity, that you are writing in your scale of gravity, the physical effect of this quantum gravity will always be reduced by the square root of number of particles that exist in your model. Otherwise, if you are able, let's say, to go above this scale, then you will produce black holes, etc. I mean, it's related also to one modern topic in quantum gravity, which is called the weak gravity conjecture. You cannot have a force that is weaker than gravity. So this is the same kind of argument. So if you have many spaces, if n is very large, okay, in the standard model, you can count the number of degrees of freedom, it will be of the order of 100, let's say. But, maybe there is much more than the standard model in life, right? And people have tried to go to very extreme case where n is actually 10 to the 32. So you just imagine 10 to the 30 copies of the standard model. So we have seen one sector, but it actually exists in 10 to the 30 copies. Then the fundamental scale, so the maximum UV scale that you will be sensitive to will be actually the TV scale and not the Planck scale. So if we 10 to the 32, this gives you 1 TV, right? And in this case, the maximum energy of the particle in the loop will be 1 TV, so there won't be a hierarchy problem anymore. Okay, maybe it's a huge price, to have to introduce all this new particle that we haven't seen to actually solve the hierarchy problem. What else? There is also something which is maybe related to this. It's called the entropic principle, which is coming again from string theory. Say, well, at the end of the day, yes, there is fine-tuning. But it's just an accident of nature, and it can happen simply because there are many universes. I don't know. For me, it's not a solution to the hierarchy problem, but maybe we have to accept it, right? It can be a fact, and we need to prove that indeed there are many possible vacuums, and we end up only in the one that allows, for the structure to form. Right? If the weak scale were totally different than what it is observed experimentally, then the physics will be totally different. You won't be able to form atoms, you won't be able to form planets, nothing. So nobody will be there to discuss the hierarchy problem. So that's what is called the entropic principle. And it's one possibility that we have to look at seriously and try to find experimental evidence of this entropic principle. So of course this is well motivated, let's say, by string theory again, where string theory somehow when you try to compactify all these extra dimensions, you end up with something like 10 to the 500 vacua. So it's not surprising that one of these vacua, have exactly this constellation between the Planck scale and the weak scale, and we are living in this vacuum. How to prove that there are all the possible vacua? That's an open question. I don't know. So I don't know if it's a solution, but maybe we have to look at it. Maybe it will be a big revolution in physics if indeed we prove that nature is accidental and there are all these vacua or all this multiverse that have a rich physics also. Another solution of the hierarchy problem was simply to say the X doesn't exist. That's what is called technicolor. So in technicolor, you break electroic symmetry without the X boson, just by strong dynamics. Of course, nowadays this is ruled out because we have observed the X boson. So the X is there. We still don't know if it's a fundamental particle, so whether these quadratic divergences make sense or not, or whether it's a composite particle, in which case, the quadratic divergences will be screened by the compositeness scale. So this is still an open question, but not having an X at all is by now excluded.
Well, maybe we just found some scalar with properties very close to the Higgs, which is not the Higgs. And then
Well, there is good evidence that what we have observed is very similar to the Higgs boson. I discussed that. I mean, we know, again, there is one strong prediction. I mean, what do we call a Higgs? Is really a scalar field that couples, to the particle proportionally to their mass. Yeah. So you can say, well, I mean, we haven't observed so many coupling of the Higgs. Well, we know the coupling of the Higgs, let's say, to the top quark, to the W, to the Z. To the bottom, we don't really know. We have some indication that it coupled to the tau and to the muon. And what we know for sure, so we don't know exactly the coupling of the Higgs to the tau and the muon, but we know for sure that those coupling cannot be the same as the coupling to the top quark. So we know for sure that the Higgs is not like a Z that coupled universally to all the families. No, we need really a relation that suppresses the coupling if the mass is suppressed. So it looks like a good indication that it's a Higgs boson. Could be some deviation, by of order 10% away from the standard model prediction.
By the way, Christophe, today the seminar at CERN about observation of Higgs decay to tau by CMS.
Yeah.
What next week?
I don't know. I received the email. The other things that we will discuss, that's some interesting new ideas, which is called the relaxion. So you want to couple actually the Higgs with another dynamical field that will have an interesting dynamical history during the expansion of the universe. So the original model actually was introducing what is called the axion of QCD. It is there to explain why QCD doesn't break CP. Right? In principle, in the standard model Lagrangian, you can write a term that is breaking CP, the CP symmetry, which is this one, G mu nu squared, except that you introduce epsilon mu nu or sigma. And this is what is called the theta parameter of QCD. And this is a term that breaks CP violation, that breaks the CP symmetry. And one consequence of this term is that it should generate large electric dipole moment, right, for the quark. And something that hasn't been observed, so you have huge experimental constraint that this parameter here should be smaller than 10 to minus 10. And one way to explain that dynamically is to introduce what is called an axion. So this is an idea of Peche, Quinn, and Wilczek, maybe Weinberg also. That say that this parameter actually is not a parameter, but it's a field. And this field has a dynamics, and a minimum of the potential. Minimum, it has a particular potential, and it reaches actually its minimum at 0. So that's a dynamical explanation why this parameter is small. And then the relaxion idea was simply to couple this axion, so this field here, to the X in such a way that what you write in nature is X squared, and the mass of the X itself depends on the value of theta. So you have mh plus theta. And when theta takes a vacuum expectation value, it contributes to the X mass. And now you can play with the cosmological history of the universe and see that actually theta at some point, will in a sense, screen the large quantum correction to the X mass. We will discuss that maybe in more details tomorrow. Tell you exactly the dynamical example and the back reaction that will stop, the evolution of the system once you reach basically the value which is close to the one that we observe experimentally. So it's a nice dynamical system with a fixed point, if you want, in its evolution. Okay, so many solutions, so maybe I can still add one. So people have considered also the possibility, let's say, that the standard model actually is scale invariant. So Gleb discussed scale invariance, Weil rescaling, etc. And the idea was to say, okay, maybe the standard model itself is a scale invariant theory. And if it's scale invariant, it means that you shouldn't write any dimension full parameter in your Lagrangian. So in particular, you shouldn't write a mass term for the x. The only term which is allowed are marginal operators, so this means operators with a coefficient that are dimensionless. So basically for the x, it will be only h to the 4. So h to the 4 is a scale invariant operator for the x. This is an interesting idea, but it doesn't really work as a scale invariance. So scale invariance will forbid directly the mass of the x, and then mh will be 0 until you are breaking scale invariance. So it doesn't really work because in this case, scale invariance is a purely classical symmetry. And we know that the standard model, breaks this scale invariance at the quantum level by, for instance, the evolution of the gauge coupling. So what you could do is maybe indeed embed the standard model into a conformal theory. So you add extra particles in such a way that the beta function at the end of the day becomes exactly equal to 0. But what you will notice is actually that you need to introduce this new particle to change, the beta function. You need to introduce this new particle at a scale which is again close to the weak scale. So since you are expecting again new physics at the weak scale, somehow to cancel these quadratic divergences. And we haven't observed this new particle either. So I don't know, probably is not a good solution. But okay, we can still put a question mark. This is still, maybe some of you will have bright ideas actually in this direction. And of course, you cannot use, another thing is that you cannot use a classical symmetry to forbid any term in your Lagrangian, because it's only, what dictates the quantum terms is really the symmetry at the quantum level. So you cannot use a classical symmetry to dictate what the structure of the quantum term that you need to introduce to regularize all this quantum corruption. Various things that don't go into the right direction. Okay, so we try to explore some of these models. So certainly not in details. Probably each of these points here will need a full lectures to really give you an idea what it is. In particular, supersymmetry is an idea which is around since 30, 40 years. There have been, I don't know how many papers, 5,000 papers maybe, on the MSSM. Clearly, I cannot explain all this in great details. And maybe one thing that you have to remember about supersymmetry, something that you will hear sometimes, is that supersymmetry is just the square root of the translation. Simply because when you are taking the commutator of two supersymmetric transformations, Q bar, these are some generator of supersymmetric that are fermionic quantities. You need to take the commutator, and two of these actually generate a translation, so sigma mu and p mu. Where p mu are just the generator of the translation. So this is why sometimes you are saying simply that supersymmetric transformations are the square root of the translation. Okay. Good. So what I'm planning to do now is maybe spend a little bit more time on this composite X and pseudo-Goldstone boson idea. Try to describe the physics of this model, come up with an explicit realization, discuss the phenomenology, and I guess tomorrow we can discuss relaxion, and we can also discuss extra-dimensional model, briefly, because there will be a lecture, a full lecture devoted to extra dimension, large extra dimension, Randall-Sundrum models, etc. So I will just say a few words, also because there is, at the end of the day, thanks to the ADS-CFT correspondence, there is a nice relation, with model in 5 dimensions and those composite X models. You can see them as the same description, or the different description of the same physics. So let us come back now to the composite X model. And the simplest composite X model is based on a large global symmetry that I've already mentioned this morning, which is simply extending this SO4 over SO3 symmetry that exists in the standard model. So SO4 was this SU2 left cross SU2 right symmetry that we discussed. It was broken spontaneously to SU2 diagonal, which is SO3. So that's the standard model. And this produced exactly 3 Goldstone bosons, 3 PGBs, that are identified physically as a longitudinal component of the W and the Z. Right? So the simplest extension, the minimal extension, was simply to consider SO5 over SO4. So this contains, in this case, 4 Goldstone bosons, right? SO5 is dimension 1/2, 5 times 4, so this is 10. SO4 is 1/2, 4 times 3, this is 6.
Christophe, excuse me, I just
Yes.
then ideas. Sorry, I interrupt you. Ideas of little Higgs models are completely gone, or they're somehow embedded in one of your.
Little X, they are somehow fitting there. The little X model, they are not trying really to cancel the quadratic divergences, they are just trying to say that they occurs at 2 loops only.
Yeah, so you somehow to move this cutoff a bit.
Right. So this means that you don't need, a new physics at the TV, but maybe you can push it to 10 TV.
But still, it's a way somehow to.
Yeah, the only thing is that somehow the little X prediction was, that it will produce a large quartic coupling. And now, from what we know from the mass of the X, the quartic of the X is of the order of 0.1, so it's not that large. So this means that the little X model are not in such a good shape. And we just
we didn't measure quartic coupling.
Well, not directly, but you measure the quartic. Not in the you measure it in the unbroken phase. I don't think.
Okay.
Just a variation. Yeah. There are various variations. What is called also the twin X model, right? Twin X model is model where you're trying to introduce new physics to cancel those quadratic divergences, but this new physics will be actually neutral under the standard model gauge group. So all these models somehow will introduce new physics, new particles close to the TV scale, and these new particles will carry some QCD or QED charges. So this means that you should produce them at the LHE and they should decay into particles that you will see in your detector. So the twin X idea was to say, well, maybe it's a way to cancel these quadratic divergences with new particles that are totally neutral under the standard model gauge group. And this way, it's much more difficult to produce them, and they cannot decay into quarks and to jets, right? Because you don't carry QCD numbers. So this means that, yeah, there is new physics at the TV scale, except that it's very difficult to see it, to see this new physics in your detector at the LHE. Dark matter. Dark matter. Yes. Yes.
Is it difficult or impossible if these new particles don't interact with standard model particles at all?
Well, at the end of the day, it does interact with the standard model through the X boson, right? But it's just that they don't carry QCD or QED numbers. At the LHE, everything which is not QCD charged, is difficult to observe. Like the X boson, and the X boson is not charged under QCD, and it was really difficult to find it because it's just buried into the huge backbone. Okay, so that's twin X. Okay, so let us come back here. So here we need to do a little bit of group theory, to describe actually what is this the Goldstone boson of SO5 over SO4. So we expect indeed, just by counting, that's very easy. You expect something like a fourth Goldstone boson that in principle will transform indeed as a doublet on the SU2 symmetry, which will be a subgroup of SO4. So that somehow has the right quantum numbers to be identified with Higgs boson. But that's something we want to see explicitly. So for that, I need to write the generator of SO5, the generator of SO5, and the generator that will survive the breaking to SO4. So SO5, so let's say the fundamental representation, will be 4 by 4 matrix, and then there will be an extra column here. Right? So here you will have SO4, you will have an extra U1. So what are the generator of SO4 in this case, which are also equivalent to SU2 left plus SU2 right? So let me say that the generator TA, the element of the group, we write it as R exponential I TA, and this has to be a matrix such that its transpose is also the inverse. That's the definition of the SO group, right? So this means that TA, so if you expand it, it's I TA transpose plus TA has to vanish. Right? So this means that the generator with this I in front of it should be anti-emission, anti-symmetric. R is anti-symmetric. And you also want a real matrix, so it has to be purely imaginary numbers. Imaginary. Okay. So, let's say we have TAIJ with the left or the right, so the two types of generator, which is minus I over 2, 1/2 epsilon ABC, delta BI, delta CJ, minus delta BJ, delta CI. So this is anti-symmetric, in I and J. And A, so A should be A, B, and C are numbers that can go from 1, 2, or 3, right? So you have the free generator of SU2 left or SU2 right. So SU2 left will have a plus, and SU2 right will have a minus here, which is delta IA, delta 4J, minus delta IJ, delta 4I. So you can write explicitly those matrices. You can open Mathematica, type those matrices, and check the algebra, right? So in particular, if you say TA left, you generate a TA left, TA right, D, I, epsilon, A, B, C, D. So they satisfied the SU2 algebra, right? And they also normalize in such a way that the trace of TA, TB is equal to delta A. So these give you the sixth generator of SO4. So this is the unbroken generator of SO5. So this is TA. And then you have the element of the coset, so the elements that are broken, SO5 broken to SO4. So this should be the 4 four broken direction, and this is simply T A hat. So A hat will be equal to 1, 2, 3, or 4. 1, 2, 3, 4. And this is equal to Ij minus I divided by the square root of 2 delta at A delta B and delta 5 J minus delta A at J delta 5 A. So those generators are really the PA at just off diagonal elements, 0 here, and just tie the 2 in the position A. It has to be anti-symmetric. And you can check, okay, it's obvious that they commute, right? They commute with S also. Okay, so now with that, we can really now build explicitly the Ghost-on boson, that will parameterize this coset space. Right? We can write explicitly what the Higgs boson is. So, as usual, when you are dealing with the Ghost-on boson, you should say that you are using the broken generator. So, I T A hat H A hat. I should put a scale, which is the scale of the breaking, the typical, the equivalent of f pi of QCD, so the Ghost-on decay constant. Right? And then you're acting on the vector that is breaking the symmetry 0, 0, 0, 1. Okay. So now you have really the description, of the 4 Ghost-on boson that form the full Higgs doublet. And the 4 Higgs doublet is 4 real scalar fields, and these are the 4 Ghost-on bosons. Okay. So what is the Lagrangian that will describe those Ghost-on bosons? Well, as usual, you want to write simply the minimal Lagrangian that you can do, which is f squared, the trace of d mu sigma dagger times d mu sigma. And the claim is that this will contain, certainly the Higgs potential, when you expand this in power of the Higgs boson, you will generate the Higgs potential, and it will also contain the interaction with the gauge field, because of this covariant derivative, which is acting on this exponential, and it will induce a coupling to the Higgs boson. So now what we want to do is actually write explicitly what this Lagrangian is. This is Lagrangian, and maybe there is a normalization factor that I don't remember now. Anyway, you choose this normalization factor in such a way that this pion, or this Higgs boson in this case, are canonically normalized. Exactly what we did with the pion in the standard model. Okay. So to simplify my life here, I will already go into the unitary gauge where, let's say, 3 of these Ghost-on bosons are heated to become the longitudinal component of the W on the Z, such a way that I will keep only the physical Higgs boson that remains in the spectrum. So out of these 4, 3 becomes the longitudinal component, and I'm left only with the physical Higgs boson. And let's see, which is the direction that makes your life easy. I think it's T3. And you need also to normalize things easily with the square root of 2 T3 at time, I think it's square root of 2 I H, maybe I have too many I, don't know. Too many I's, yeah, maybe this I is not there. And I'm not sure what is square root of 2. Doesn't matter. anyway, when you are computing explicitly this exponential, so you have T3, you know what it is. It's acting on the vector, so you can compute explicitly this exponential. And in this case, it will be simply this sine h over f 0 cos h over f. Follow my notes, every square root 11 factor 1 half. In such a way, again, when you're looking at, when you're expanding this exponential, you will find first term which is e mu h squared, and then you have an interaction between the w which is contained in this derivative and this p. And if you write explicitly, it will be minus g squared f squared divided by 8 sine squared theta h over f times w mu. Yeah, for here I've put g prime equal to 0, but again, it's easy to reintroduce g prime. So you already see some deviation compared to the standard model prediction, right? In the standard model prediction, you add simply 1/2 d mu h squared minus 1/4 g squared v squared w mu a 1 plus h over v squared, right? So that was the standard model Lagrangian. So here this is the Lagrangian of this minimal composite X model, MCHM. So you see some difference, right? Here there is this sign instead of having simply a polynomial expression.
Yeah, but from the other hand, somewhere you already neglected next terms in 1 over f expansion. But in sign, you kept it. So how to understand?
Not really.
So you can expand the sign.
No, here, I mean, there are various things that you're expanding
But the field touch could be very large. You see, in derivatives, you made an expansion, yes. But here you kept all terms. So how is this consistent?
Yeah, so, I mean, here you can do the matching. Here the extra term in the f will also involve extra derivatives. Right? So here I'm comparing the Lagrangian at the same level of number of derivatives. Right? So it's true that there will be more derivative interaction, but for the moment, I mean, they are not there in the standard model. What I want to say is that already at the p squared level, so with two derivatives, I still get a structure, a prediction of the X coupling that are different. And I want to do the matching, right? I want to do the matching between those two Lagrangian and see what are the physical difference in the prediction of the couplings. So for that, you need to do the expansion around the vacuum. Okay? So this is something that I haven't written there yet, but at the end of the day, you are also, I mean, in addition to this Lagrangian, you have the potential for X, in such a way that the X acquire vacuum excitation value, and you need to expand around the bed to compare with this Lagrangian. Maybe I'm using two different H, right? Here, H is really the fluctuation around the bed, so X plus H. And here, I already included the bed in it. So not the best notation. So let us do that. Let us look explicitly at the expansion of this sign, right? And the Lagrangian of MCHM, which is minus G squared F squared over A. If I'm using the the real representation, I should also have this one up. Sign. So what I want to do is to say that H is just a value plus a fluctuation around its background expectation value. And I want to look at an expansion in power of delta H to be able to do the matching with the standard model Lagrangian. Okay, so that will be sine squared H plus delta H over F times W mu squared, W mu sorry. So what is this thing? So this is sine squared of the valve H plus the derivative of sine squared theta is 2 sine theta and cos theta. Derivative of sine is cosine times delta H over F. Then you need to go to the quadratic level. Okay. So the derivative, the second derivative will be equivalent. So this is also sine 2H over F. So the derivative will be 2 cos 2H over F, 1/2 for the expansion, delta H over F squared, plus. Okay? And cos 2 theta is cos square theta minus some square. Let's say 1 minus 2 sine squared H over F. If I remember trigonometric relation. Okay? So this Lagrangian is what? It's minus G squared S squared over A sine squared H over F that will be factorized 1 plus 2 cos H over F divided by sine H over F delta H over F plus 1 minus 2 sine squared H over F divided by sine squared H over F delta H of F times W squared. Okay? So now you want to make the identification or to make the analogy with the standard model Lagrangian. So first of all, you want to say that this is, just identify the mass term, that will be identical to 1 over A G squared V squared. Okay? So now you know actually how to interpret, how to relate what you call the value of the X in the standard model to the expectation value of this X field. Right? That's the first relation, that V is nothing else than F times sine of the value of the X divided by F. That's the first relation. So if you want, the sine of this, the sine of theta, whatever, is just the ratio of the width scale divided by the compositeness scale of the proportion. So what about these things? So F times sine is nothing else than V. Right? This is V. And here, cos is the square root of 1 minus sine squared H of squared. So this is square root of 1 minus d squared of f squared. Okay. And here this is v squared. And here this is simply 1 minus 2 v squared over f squared. So your Lagrangian now is very similar to what we have written yesterday, with A and B parameter. The Lagrangian is nothing else than minus 1/2 the mass of the W, and W squared, that's 1 plus A, that's 2A H over B, plus B H squared V squared, right? And now you say that A is actually square root of 1 minus D over F squared, and B is 1 minus 2 V squared of F squared. So we have been able to really compute this Lagrangian in this SO5 over SO4 model. So now you have really a prediction of what are the X coupling in this model. And you get some deviation away from the standard model. In the standard model, A and B are equal to 1. And here they receive a correction that scale exactly as we predicted yesterday. The correction to the standard model prediction scale like V squared over F squared. So the ratio of the weak scale divided by the scale of the composite interaction, compositeness scale of the equals. Okay. So far so good for the coupling of the X to, let's say, to the gauge boson. So the next thing that we need to explain, that I need to tell you, is actually how to introduce fermion into this picture. Right? So what you want to do is certainly to embed, the standard model quark and leptons into representation of SO5 in order to be able to couple them to the sigma matrices in a way that respects this SO5 global symmetry. And for that, you actually need to introduce extra fermions to complete the representation of SO5. So exactly like in supersymmetry, you need to introduce new fermions to make the theory invariant under the supersymmetric transformation. Here, you need to introduce also new particles to make the theory invariant under this SO5 global symmetry. So in supersymmetry, the particles that you need to introduce have different spin. Let's say for the top, you introduce two scalar fields, which are called the stops. Here, the symmetry is just a usual global symmetry, so it doesn't mix the different spin. So the partner of the top quark will be actually new fermions. And we want to characterize a little bit the masses and the charges of these new particles. So we will see exactly how to derive the electric charge of these new partners associated to the top quark. So for that, you need to look at how, for instance, a fundamental representation of SO5 will decompose under SU2 left plus SU2 right plus U1. So at the end of the day, I also need to add actually an extra U1, and this will decompose into SU2 left.
Also global U1?
Yes. I mean, at the end of the day, you will charge a subgroup, you will gauge a subgroup of this global symmetry.
That's what you want.
That's another story. So the hypercharge, actually the hypercharge in this case will be a combination of this U1x and the U1 which is contained in SO5. So it's hypercharge. So this is very similar to this Gell-Mann-Nishishima relation that was relating the electric charge to the hypercharge on T3 left. So here we are relating the hypercharge to the U1 charge and the T3 of SO5. So the hypercharge is T3 right plus X, where T3 right is the U1 of SU2 right. In such a way that the electric charge, you can compute it, is T3 left plus T3 right plus X. So now if you have a particle which is a fundamental representation of SO5 with a charge X under the U1X, this will transform actually as a doublet on the SU2 left with a charge which is X plus 1/2, another doublet with charge X minus 1/2, and a singlet with charge X. If you like group theory, I can tell you exactly the embedding, of all this representation into SO5. You can check for yourself. So you have Q plus and Q minus, which are those two objects. Q minus 1/2, the minus Q plus X plus 1/2, minus I QX X minus 1/2 plus Q plus X plus 1/2, Q plus X minus 1/2 plus Q minus X plus 1/2, I Q plus X minus 1/2 minus Q minus X plus 1/2. And then you have the singlets. So that's really the embedding, of these two doublets, Q plus and Q minus, and the singlet into the fundamental representation of SO5. So if you want, if you want to play with group theory, you can check, indeed, now you have the generator of SU2 left, you can check that indeed Q plus transform exactly as a fundamental representation of SU2 left, Q minus also, and then the singlet is uncharged under this SU2 left. So it's nice to play with matrices and check that everything follows the rule of group theory, if you like. So, now what do you do with the top, the bottom, etc. Right? So how do you want to embed? Shouldn't have a record. Doesn't matter. You can do it yourself.
Yeah.
So, for instance, you want, to embed the top right into the singlet.
So, why did you start from SO5? Just for simplicity, or a simple solution?
It's a minimal. Okay, you have SO4.
Yeah.
So you extend it to SO5.
But you have millions of other possibilities.
You have, there is not so many coset space that will give you only 4 ghost on boson. Right? Yeah. So that's, I don't know, maybe there is 2 more, I think, SP something. We have expert group theory, maybe they know. What are the coset that give you 4 ghost on boson that also contain SU2 cross U1? Be able to gauge the standard model symmetry, right? So not so many options. So I think this is a minimal case. In other model, you will have the X, but you will also have extra boson bosons. It's possible. Different models. Okay, so I want to say that we will embed certainly the top right into these things, and we could embed, for instance, the Q left into this doublet here. And for that, I think you need probably to choose X to be equal to 2/3, right? So this means that in this case, you are also expecting, new particle here that are completing this fundamental representation. So you are expecting new particle with a charge that should be plus or minus 1/2 for T3 left, plus T right, which is plus 1/2, plus X, which is 2/3. And so you are expecting a particle which has a charge 2/3, an electric charge 2/3, and the other will have 2/3 plus 1/2, that's 5/3. So that will be the new top partners. So you expect at least two new fermions, one with an electric charge 2/3 that transforms as a doublet, and another one with an electric charge 5/3 that also belongs to a doublet of SU2. So this is really an exotic quark. It's a new quark with a charge 5/3, which is predicted by the global symmetry. And this object, capital T, will decay, for instance, into a W and a regular top quark. Okay. Does it work? The 5/3 is 1 plus 2/3. Okay, good. So that's one of the beasts that you expect to see in your detector. And people, I mean, Atlas and CMS experimentalists are searching for these new quarks, 5/3, that decay into this way. It's nice search with two same sign dilepton, for instance. I mean, the good thing is that this object, they carry QCD color, exactly like the top, right? Because this is a triplet under QCD. So this means that this object, this new quark, should also be a triplet under QCD. So they can be produced by exactly like the top is produced at the LHE, but purely by QCD. And then you're searching for the decay, so you can pair produce this object in the same way that you're producing a pair of TT bar by QCD.
And these objects are pair, not vector-like.
At the moment,
because what experimentalists are looking at vector-like.
Yes, so
these charges.
Yeah, we need to explain how they get their mass, right? At the end, they are vector-like, but still they couple to the X. So they get their mass mostly from another source than the X wave. So they are vector-like, and then they still couple to the X. So they are produced, exactly like TT bar, gluon, right? Gluon, are produced this capital T just by QCD interaction. And then this T will decay, as I said, to W on top. Not making a mistake. The TT bar, W plus, W plus, W minus, TT bar. The W decay into W on bottom. W plus, here it's W minus on bottom. And then you look at the leptonic decays of the W, so you will reconstruct the final state with two same sign leptons. So that's again something that is very easy to disentangle from background, so it's very easy in principle to search really for this object. And now there is even some bound which are exceeding 1 TeV, for instance. So we know from the LHE that there is not such an object with a mass below, I think, 1.2 TeV or so. So that puts some constraint, of course, on the model, in particular on the compositeness scale, F, or also in the typical coupling of the strong sector. That's something I will tell you about. So now, how do you give the mass to this particle in a way which is invariant on the SO5? You can write something which is T bar left, sigma transpose C right. So that was transforming as a 5, so this is invariant under SO5, this is invariant under SO5, so that's fine, and this gives you a mass term. And at the end of the day, you know, when you expand psi with in power of h, this will give you actually a mass term for Lagrangian, contribution to the Lagrangian, which is, so you have mass here, m, sine 2h over f times t left, t right. So again, you can repeat exactly the same exercise as we did for the gauge boson. So expand h around its valve, and then you will generate the coupling of this fluctuation, so the linear field, to the gauge boson. And in this case, you will get actually that you have the mass of the top, as usual, divided by the square root of 2, the mass divided by the valve of the standard model. T left, T right, so maybe a bar somewhere, you know. 1 plus parameter C in this case, delta H over V, and you can compute that C is equal to 1 minus 2 V squared over F squared divided by square root of 1 minus V squared over F squared. So that's a prediction of this SO5 over SO4 models. So you expect some deviation of the top Yukawa coupling instead of 1 as in the standard model. So in the standard model, C is equal to 1. So here you get some deviation that again are controlled by V squared over F squared, particularly if you go to the limit of large compositeness scale. So this is 1 minus 3 half V squared over F squared, right, plus the 12. So you get a deviation which are controlled by the same parameter. So that's one prediction, so deviation of the X coupling, and the other prediction is the existence of these top partners. So that was, you know, one particular embedding. So here I was really trying to embed, let's say, the top and the bottom into the fundamental representation of SO5. So this is what we call minimal compositics model 5. 5 simply because you put them into fundamental representation of SO5. There are variants of this model where you are trying to embed into antisymmetric representation of SO5, which is 10. So 10 is just antisymmetric representation of the 5. And in this case, you get a slightly different prediction. So for instance, in this case, if you do this, the same exercise, you will find that C is equal to A. So 1 minus V squared over F. So, you know, somehow you have some prediction for all this deviation of the X coupling that are really dictated by the geometry, right? It's just the consequences of the symmetry, right? So it's not arbitrary function. These functions are really the consequences of this symmetry on the embedding of the quark into representation of SO5. Is there any questions? It's a little bit technical, but at least you get a feeling exactly how those computations are done.
Could you please explain, you have a real representation of SO5?
Yes.
Really, SO5 is a real group.
It's a real
and
group, yes.
its irreducible representations are real.
Yes.
And it means that you have 5 real numbers, a vector of 5 real numbers.
Yes.
And then you have 2 complex representations plus 1 complex U1 representation. They do not come together. Either you have a complexification of.
So this means that probably those are complex conjugate to each other, right? So you have two doublets.
It these are different representations. I cannot. Either you have two. You have then you should say, as you have said many times, that you work on the level of Lie algebras, and on the level of Lie algebras there was no problem. Then you say that you complexify the Lie algebra of S O5,
Yes.
and in this case you can have an irreducible 5-dimensional representation of this Lie algebra complex.
Yes.
Because if you
Yes.
introduce complex generator, then the two representations can merge to give one irreducible 5-dimensional complex representation.
Yeah, that's probably.
And I do not understand the line right above. So it is a reduction of.
Yes.
Then it should be an arrow, not equal.
Yeah, I mean, yeah, sure. I mean, it's just how this representation decomposes in the SU2 plus U1.
But then it's a reduction. You cannot equate these two groups. They are not equal. Just.
I don't know.
No, this is all right. This is the decomposition, but
this
the line above.
Yeah, sure. Yes, included, right?
Usually it's written just an arrow that you reduce to this reduce this group to a subgroup.
You're fully right. Yeah, this equal sign was.
Christophe, another question, as you said, we are physicists, so we have numbers, right? So suppose your parameter f is about 2 TeV.
Yes.
V is about 200.
Yes.
Okay, V over F
1%.
It is the effect is 1%.
Yes.
In measurement of Higgs coupling. So how far we will be able, how quickly we will be able to measure Higgs couplings to that precision?
1%. You need to wait.
Up to linear collider.
ILC reach 1%. If you are able to push LC to 500 GeV or maybe 1 TeV, which cost 5 extra billions. At the moment, the Japanese are more thinking about the ILC at 250 GeV, so purely a Higgs factory. And then you are barely reaching the 1% sensitivity. So
the effect is very, very right.
Yes. I mean, the current LHC measurement, are constraining F. So 10% deviation, so F is typically above something like 500 or 600 GeV.
Yeah.
Which is also kind of what, you are probing directly by looking at these top partners. So depending a little bit on the parameter that, relate the mass of the top partner to F. So here you need a coupling. Depending on the value of this, we have the same sensitivity. Yeah, so it's very difficult indeed to exclude the compositics. You need a lot of energy and you need a lot of precision. So that's why this compositics model will survive a long time. Nonetheless, maybe that's something I can mention. There is indirect effect due to electric precision data. Because here, we are probing a deviation of the coupling of two W's to the X boson. So this means that this will have an effect. So this is not the value predicted by the standard model. So this will have an effect on the way the W and Z propagate. You can draw some loops. And actually that's what is giving you the strongest constraint on compositics model at the moment. So I need to mention that. You can close some loops and draw some nice diagrams. So there's a contribution to what is called S and T. So S is just a mixing, a kinetic mixing between the W and the B. So you can write it in terms of dimension 6 operator in the standard model as W mu nu A, B mu nu, H dagger, sigma A H. Right? So this is a dimension 6 operator, the standard model. So this is perfectly invariant under SU2 cross U1. And once the X take a vacuum expectation value, this will induce a kinetic mixing between W3B and B min after electric symmetry breakings. Once you give a valve to the X. So this means that here, so you have P squared, right? Momentum dependence propagator. So the way the W and the Z propagate are modified by this operator. And this is highly constrained by electric precision data from lab. So basically this constrains the coefficient in front of this dimension 6 operator. And the claim is that if the X coupling deviates from the standard model prediction, then you end up with a log contribution to the one-loop correction to this propagator. So for instance, you have two diagrams that contribute here. You have the exchange of the X, the exchange of the pion, the boson, it's W3 and B. So that's one contribution. And the other is just pi plus here is pi 0. You can also have some charge pion, pi plus, pi minus. You can compute these diagrams in the standard model. Each of them are logarithmically divergent. And this logarithmic divergence actually cancel with each other, provided that the coupling of the X to the W and the B are the one predicted by the standard model. If not, you end up with a log divergence, which is 1 minus A squared. Again, this A, which is the coupling of the X to the W, times the log of lambda squared, divided by the mass of the X boson. So it's only for the standard model that this log cancels. And now, given the fact that S, what we call S is a coefficient with a proper normalization, so S has to be smaller than 10 to minus 3, gives you actually a bound on A, and then it gives you a bound on the compositeness scale of the X boson. So F has to be bigger than this. And if you put the number, the constraint that comes from here is actually stronger than the constraint coming from the X measurement. So it's something like, I don't want to give you wrong numbers, but it should be something like 800 GeV. Of course, this is indirect, so it could be that also you have extra source, that could contribute to S, and then you could have a small cancellation between those two contributions. So this is not so robust as the measurement of the X coupling deviation. But still something that is there, that exists. Okay. Yes. So now we started really to do the connection, let's say, with higher dimensional operator that I've already mentioned yesterday. This what is the correspondence between A and a dimension 6 operator that you can write to the standard model Lagrangian. I write this correction to the X kinetic term. Now it's time probably to look into more details about what are the full list of operators that you can constrain, and what are the constraints on those different dimension 6 operators. So the rule of the game here is simply to write, all the possible dimension 6 operators that are gauge invariant under SU3 cross SU2 cross U1. And you want to build this operator with a standard model field. And so there are various operators that are constrained, like this one, for instance, that was one example, that are constrained in the vacuum. So when you replace the X field by its vacuum expectation value, this operator has a physical effect, which is modifying the propagator of the W on the V. So this is constrained by LEP, by precision measurement of, let's say, of the Z boson, or the Z interaction with the quark on the lepton. These are easily constrained. There are other operators on the other hand that are totally unconstrained if you don't excite the Higgs boson. If you are unable to produce the Higgs boson, they will remain totally unconstrained in the vacuum. And this is the case, for instance, of this type of operator, H squared times G mu nu, right? So I claim that this operator is unconstrained if you replace the X by its vacuum expectation value. Okay? Simply because, okay, this will be, in addition to the usual kinetic term for the gluon in the standard model Lagrangian. So clearly, if you replace the X by vacuum expectation value, what you obtain is simply a correction to the kinetic term of the gauge coupling. So something, kinetic term of the gluon, something that you could also absorb in the gauge coupling. So sometimes, you define the field strength the normalization of the gauge boson in such a way that the only dependence on the gauge coupling is in front of the kinetic term. Right? That's a canonical not canonical, but a nice parameterization, because then this is the only place where the gauge coupling enters. Right?
It's non-perturbative
relation. Yes.
So, solitons and
soliton, instanton.
Useful for perturbative calculations.
If you're doing non-perturbative QCD, that's probably what you will be using.
Exactly.
So clearly here, we see that the only effect of this dimension 6 operator, so this is divided by a scale, right? The only effect of this operator will be simply to change what you call the strong coupling, right? So what we'll be calling the standard model gauge coupling of SU3 will now be GS plus PS squared plus V squared over lambda squared. So you are just changing the input parameter of your Lagrangian.
This coupling is measured very well.
Yes, it's measured, but this is an input parameter, right?
But this parameter enters not only here, but also in the interaction with fermions.
No, the only place where it enters is here. With this normalization, this is the only place.
This is a normalization. This is the so-called geometrical normalization of the gauge fields, and the coupling constant stands only in the denominator of the action of the gauge fields. And I've said that it's not suitable for perturbative calculations. To make perturbative calculation, you have to rescale all the fields.
It's simply change.
Should be rescaled. Yes, exactly.
G mu, call it G
Exactly.
tilde, right?
Exactly.
This is canonically
Yes.
normalized.
And then the constant appears in all the interactions.
Right. So the claim is that here, in the vacuum, so when I replace X by its vacuum expectation value, the only effect of this operator is simply a shift of the input parameter. What you call GS in the standard model now corresponds to 1 over GS plus V squared over lambda squared. So it has no physical effect. Right? It's just an input parameter that is changing in your Lagrangian. So this means that in the vacuum, so without the Higgs boson, there is no way actually to constrain this operator. You need a Higgs boson to be sensitive to this dimension 6 operator. And of course, this operator in Higgs physics has some big influence, right? Because now you have a contact interaction between two gluons and a Higgs boson, right? So this gives you an additional contribution to the Higgs production, which in the standard model proceeds by this loop of top quark, right? So here you have a physical effect in Higgs physics. So that's one example, of a deformation of the standard model that you are sensitive to only in Higgs physics. You need to produce the Higgs boson to see this operator, to see this deformation. So that's one example, of the kind of information that we have learned in X physics, what are really the constraints of this dimension 6 operator? So you can ask yourself how many deformation of the standard model were unconstrained before the X was observed. So what are really the additional information that we have gained by accessing the X boson, that nobody will have been able to put any constraint before the observation of the X. While the number of such deformation is equal to the number of input parameters in the standard model. So you can always redefine all your input of the standard model, absorb them by some higher dimensional operators, and they will have no physical effect if you are unable to produce the X boson. So that was one example. The other one will be B mu nu squared. You can also attach A squared. You have also W mu nu A, W mu nu A, H squared. What else? You have, let's say, the different type of fermions. So if you do the counting, let's say for a single family of quark and lepton, right? Complex conjugate and shape conjugate. So here it was the Yukawa coupling. So you multiply the Yukawa interaction by the power of H squared. Right? So this will give you 1 here, 1, 3, because you can do it for the different type of fermion, up, the down, and the electron. 3, 6, what else? There is H to the 6. Some other term that you can write in your potential, and you can also modify the kinetic term of X, which is related to 1 and 1. So at the end of the day, you have 8 deformations that are sensitive only to X physics. Right? So these are redefinition of the gauge coupling of the standard model. This is a redefinition of the Yukawa interaction, or if you want the masses, the input parameter that correspond to the masses of the fermions. This is a redefinition of the X mass, parameter that controls X mass. And this is a redefinition of, let's say, the W mass or the Z mass, which is an input parameter in the standard model. You are not predicting the W mass or Z mass in the standard model. You need to take it from experimental data. And there is only one, because of custodial symmetry, that relates the W and the Z. So these are the eight parameters that you should really try to constrain in X physics. And how many of them are constrained at the moment? This operator, you have no sensitivity at the LHC at the moment, because the only effect.
Why 8? You mentioned 6.
Yeah, they are all dimension 6, right?
Yeah, all dimension 6, but number of this operator is 6.
It's 8. 8.
Fermions.
You close the loop. No?
No,
1, 2, 3,
4,
no,
5,
there are
6.
3. There are 3 because
Okay, you divided by the back.
Yeah, there are 3 types of fermions. I do the counting for one
okay,
family.
3 types of fermions.
Up, down, and
Yeah, okay.
and electron. So I was saying that this one control blue to X. So this is measured with 10% accuracy. This will control the decay width of the X into gamma gamma. This will control the decay width of the X into a photon on a Z gauge boson. And this is actually something that hasn't been really measured at the moment, because the branching ratio is very small. It's only a one loop process in the standard model. right? And you have to decay the Z into lepton in order to be able to reconstruct this object. So this hasn't been measured. And it will be measured at high luminosity LHC, but at the moment there are only very weak constraints on this thing. So this is, let's say, 10%. 10% at the moment is a factor 5 or 10 times the standard model prediction. This is modification, let's say, of the top Yukawa.
So why not DESY or WW from this third operator?
That will be this one actually.
Why not those?
Yeah, but they are not. I mean.
No, number 3.
This one.
3,
Yeah.
This one.
Yeah, but no, you have to take. I mean, you can already modify ZZ by this one, right? So
okay, they modify
you cannot
both.
use one. Yeah, sure. They will modify both, but
yeah.
With one measurement, you cannot constrain two operators.
Okay, in this sense.
So the constraint of ZZ, you will use it in ZZ star. You will use it to constrain this operator.
Okay.
Then you cannot use it anymore, and you need to rely on this. So white top, white bottom, and let's say white tau. Right? And this is the decay into. And this is the decay of the X or the X, the double X production. So you glue two X bosons. Yeah, those things. I mean, some of them are not so well measured. I mean, the bottom Yukawa is not so well known. The top, maybe we have to wait next week on the CMS talks. I don't know. But anyway, this is okay. We can say it is more or less measured. We can assign maybe an uncertainty of 20%. But these things, for sure, and these things, no, we have no real clue of the experimental constraint at the moment. You really need to wait high luminosity LHC, or maybe even to wait a more energetic machine to be able to produce two Higgs bosons at the same time.
By the way, Christophe, to some extent, dB Higgs was measured by Tevatron. When Tevatron observed this mode,
yes,
it's at the level of 3 sigma, 3.4 something. It was done
associated production, so you're looking at VH production with
right,
H going to
H
dB.
dB, right. At Tevatron it was measured approximately the same time when Higgs was discovered at the OHC.
Okay. Okay, you need to look at that.
Yeah, precision is not high, but
Yeah, right. I mean, certainly is not 10%. Good. Anyway, that's really the roadmap, let's say, of X physics, a measurement of these things and a measurement of the X decaying to Z and the photon. So here, actually, I focus only on the operators that are respecting CP invariance, right? So you could also do a similar counting for the CP violating coupling of the Higgs boson. You will find other operators. It's much more difficult actually at the LHC to be sensitive to the CP violating Higgs coupling simply because they don't interfere with the standard model. Right? So here all these operators interfere with the standard model. So in such a way that when you're computing, an amplitude squared for the BSM model, it will be the amplitude for the standard model squared plus twice the amplitude of the standard model times the amplitude of BSM plus the amplitude squared of BSM. So for CP even deviation, this interference is non-vanishing. But for CP odd, this is vanishing because, okay, standard model is CP even, BSM is CP odd, so there is no interference, so this is equal to 0. So this means that you're only sensitive to the squared of the BSM effect that goes like 1 over lambda to the fourth, not like 1 lambda to the square. Right? So this is an effect that goes like 1 over lambda squared, where lambda is the suppression scale of this operator. This is of order 1 to lambda to the fourth. So that's why it's much more difficult actually to constrain the CP violating deviation of the standard model. last thing that I want to discuss before concluding this lecture is actually what do we expect for the coefficient in front of those different operators, right? So what is the power counting from your for your deviation of the standard model? And to do this power counting, actually it's easier, it's better to use a slightly different basis of these higher dimensional operators. In this basis, the power counting is complicated, so the effects are distributed over different operators, so it's not so nice. While in another basis, things factorize much more nicely. So the power counting means, okay, that you have the standard model sector, you have the BSM sector, and you have some interaction between the two. So the BSM sector you will characterize by a scale F and a typical coupling G star. So it's the minimal things that you will need to describe any BSM sector. Of course, BSM at the end can be much more complicated. You can have different scale, you can have many different couplings, but at least that's the minimal set that you need to describe the BSM sector. One scale and one coupling. You need to specify what is the mass of the new particle, and you need to specify how those new particles interact with each other and how they are coupled to the standard model. So you need one scale and one coupling. So that's the minimal thing that you need to describe an effective field theory, right? One scale, one coupling. So then the question is really, what is the dependence on those two quantities for the various coefficients of these higher dimensional operators, right? So that's what we will do. So typically, if you have this scale F and this coupling G star, you will expect new particle at a mass M star, which is G star times F. Exactly like in QCD, right? So you have F pi, you have G rho, and you expect all the resonances of QCD. So let us try to write some operators. For instance, d mu h squared squared, which is one of the operators that we discussed yesterday. So the question is, what do you expect as a function of G? So how many power of the coupling do you expect for this operator? So you know that has to be a dimension 6 operator, so if you certainly put a scale, a mass scale, so G star F squared. So you can, for instance, imagine that you will generate this operator by exchanging new particle at a mass G rho times F. So exactly like when you are generating the 4 Fermi interaction for the Fermi theory, you obtained something that was going like G squared divided by the mass of the W squared times 4 Fermi side to side. So here you are exchanging a new particle of a mass G star times F with a coupling. So the question is, how many power of the coupling G star should I put in this numerator? And that's exactly where, it comes back. That is very nice to count the power of H bar. So we say that the coupling is dimensionless in natural unit when H bar is equal to C is equal to 1. Then indeed the gauge, all the coupling are dimensionless. But actually, a gauge coupling, is not a dimensionless parameter. It has a dimension which is H bar minus 1 half. So since now you want a Lagrangian to have the dimension of H bar, because you are writing simply the action. When you are doing this S matrix, you are expanding this action divided by H bar, right? So you need the action, or you need the Lagrangian to have the same dimension of H bar to make this expansion meaningful. So you see that now, the thing that I need to explain is that also the scalar field has H bar dimension equal to 1 half. So H is also true for the fermion. This is also true for the gauge field, as H bar dimension 1 half. You can do that in the exercise session. So you have 4 power of the x. So this has h bar dimension which is equal to 2. This has h bar dimension which is 0 because it's copying a product of coupling. So this means that it should go like g star squared to have the h bar dimension correct. So you expect, that this dimension 6 operator simply to be suppressed by 1 over f squared. And of course, if g star is large, so larger than 1, having a suppression which is 1 over f is much better than having a suppression which is 1 over the masses. Right? So this means that it's really a strong operator in the limit of strong couplings. Okay. So you can repeat the exercise for other operators. So there is actually 4 types of operators like that will be suppressed by 1 over f1 over f squared. This is h bar d mu h squared. This is also 4 power of the x field, so it will be 1 over f squared. There is the modified Yukawa interaction, psi bar h psi. This is 1 of f, so maybe here we can spend a little bit of time to do this power counting here, right? So again, the dimension 6 operator, right? Fermion has dimension 3 as a mass dimension, so this is h bar dimension. And then you have also to look at the mass dimension, so h is equal to 1, fermion is equal to 3r, the gauge field is dimension 1, right? That's the Y dimension, whatever, the scaling dimension that Gleb was telling you about yesterday. So here you have dimension 4, the Yukawa interaction in the standard model at dimension 4, right? So 3r is 3, it's 4, 5, 6, right? So you have to suppress G star as a mass scale. And then what is the power of the gauge coupling? So the h bar dimension in this case will be, so you have 3, 4, 4, yes, you have 5 fields. So this has h bar dimension which is 5r. Here in front of it I already put a Yukawa interaction which has h bar minus 1r. Okay. So it's h bar to the squared. So if I want 1, I need to put 2 power of the gauge coupling, 2 power of the coupling, the new physics coupling. So here I've already put, let's say, some selection rules, right? I could have chosen actually instead of g star squared times y, I could have put g star to the cube. Dimensionally, this would have been correct also. But this will be actually in trouble with flavor physics, because usually, if you put something with random flavor structure here, you will generate actually some flavor changing neutral current by the exchange of the Higgs boson. So why is that? Well, simply because you have to take into account this operator plus the usual Yukawa interaction, right? H, psi left, psi right. So that's the usual Yukawa interaction. And usually you put some flavor indices on the Yukawa interaction, so I, J, and now you have a new matrix, Cij, H cube, psi left, psi right, Ij. G squared. So now you are looking at what you obtain when you're expanding around this vacuum expectation value. You have Yj VEV plus X, psi I psi j plus Cij, and you're expanding, so you have V plus 3, V3 plus 3 V squared H. Psi I psi j. So in the standard model, the X interaction and the mass are proportional to each other. So you have a single matrix that controls the mass term and the X interaction with the fermions. So this means that as soon as you diagonalize this Yij, then automatically the X interactions are diagonal in the flavor space. So X interaction in the standard model, the X is the X coupling are flavor diagonal. But this is no longer the case, if you have here another matrix because of this factor 3. So the mass, now the mass will be Yij plus Cij divided by V squared. But the interaction of the X will be Yij plus 3Cij. And in general, you cannot diagonalize simultaneously those two matrices. Right? If they have a generic flavor structure, you have two matrices, and those two matrices, unless they commute, they cannot be diagonalized simultaneously. So this means that if you have a generic flavor structure here, you will have some X coupling that are flavor violating. So you can change the flavor via a coupling with the X. So for instance, you could have a decay of the top quark into an X plus a charm. Or you can have an X that decays into a tau plus a mu. Okay, maybe you need to put some bars. Tau plus mu bar. So that's some decays that are highly constrained by data, right? I mean, because you are changing the flavor, that's usually quite troublesome. So there is really huge constraint on this thing. So that's why, at the end of the day, it's better not to have a generic flavor structure. So it's better to have some new interactions that are already proportional to the Yukawa interaction. This is what is called minimal flavor violation. So the flavor structure satisfies this minimal flavor violation ansatz. And that's also what you get, from this SO5 over SO4 model, right? I mean, because everything was coming from the expansion of this exponential. So the flavor indices, are just in front of, there is only one operator that contains flavor indices, yes. So this means that Cij are always proportional to the Yukawa. Okay, so just, yes. Okay, so G squared in the numerator, G squared in the denominator by the H bar counting, right? So we are fine. Okay, so now we are running out of time. You can also do the counting for H to the 6. This will be again surprised by 1 over L squared. And what I want to say is that there are other operators that are actually more suppressed than those ones, so they will have some effects that are subleading, at least in the limit when G rho is large. This operator will be the leading effect for the modification of X physics. So let us just take one example. You can write, and as I say, there are many operators, right? So you can go through the list and do the counting for all of them. D mu H, D nu, B mu nu. So the claim, okay, so here we'll put a G prime associated to this gauge field, right? So let us do the counting. So again, it's dimension 6, so it has to be suppressed by G star times F. So now what is the number of field, right? So 1, 2, and 3 field. So this is H bar to the 3 half, right? G prime is H bar to minus 1 half. So this dimension 6 operator has already the right number, the right dimension in H bar. So this means that here, so here I don't need to add any extra power of the coupling. So that's really the suppression scale that you expect from this dimension 6 operator. And you see that compared to this one, there is one further G star suppression. So this means that this one, in the large coupling, in the strongly interacting limit, this operator is irrelevant compared to this one. You should really focus your attention to those ones. So that's some example, of things that you can do just using naive dimensional analysis, right? H bar counting, the mass dimension counting, you can really focus on what is the relevant physics for instance, in the limit of strong interaction, which is supposed to describe, for instance, some propositive model. Okay, so I think it's time to stop.
Yeah.
Thanks a lot.
Thanks a lot, sir. We will continue soon, right? On the seminar.
We never stop.
We never stop. Right. So we have less than 25 minutes break, and then please come back for the seminar. It's tough. Tough life.
What's the last question?